have already seen that when we say a topological space x tau is said to be a T1 space, that is if and only if you give x y in x not equal to y, then there exists an open set U containing x and another open set V. This is a open set containing y, such that x is open set containing x, but x is not, this V should not contain x, so that x is not in V, and similarly V open set containing y and y is not in U. So, but intersection may be empty. So, either they may be disjoint, or I mean if there is disjoint open set containing x and y also, I mean it has this property, there exists x here, say that y is not in U. So, that will satisfy. So, such a space we call it T1 space, and also we have seen that a space is topological space is a T1 space if and only if every singleton set is closed. And then we have seen when you say what is called Hausdorff topological space. So, Hausdorff means x y belongs to x, x not equal to y implies this open set, there exists an open set containing x, an open set V containing y, such that they can be separated, that means they are disjoint. These 2 points are separated by open sets, then we say that this should be true for every x y, whenever x not equal to y there exists open set having this property, then we say such a topological space a Hausdorff topological space. Now, let us see what we mean by a regular topological space. A topological space is said to be a regular space, that is first we will assume that our topological space is such that it is a T1 space. I mean there is a some others they do not assume that it is a T1 space. So, here we will assume that it is a T1 space. Further it has a property that whenever A is a closed set not containing x, that point x which is singleton a closed set, and the set A can be separated by open set. So, a T1 topological space x tau is said to be a regular space. So, that means regular topological space, regular space if and only if is said to be a regular space if and only if for x in x and capital A closed subset of x not containing x, such that x is not in A, then these singleton x and A can be separated by open set, then there exists open sets u comma v in capital X such that X belongs to U. It is a open set containing X, V open set containing the set A. So, that is what we have, U open set containing X, the whole V is a open set containing the set A. V is a open set containing A and they are disjoint. X belongs to U, A subset of V, first this, and they are disjoint, U intersection V is empty. Then we say that such a topological space X tau is said to be a regular space. See, by definition itself, that is the reason we assume that it is already a T1 space. Now take X not equal to Y, xy in X, assume that our given topological space is a regular space. Then for any xy in X, X not equal to Y, because our space is T1 space, the singleton Y is closed, this is closed, this is our A, and X is not in singleton Y, and hence there X is a open set U containing X and another open set V containing Y. Y is singleton, A is our singleton Y. So, hence this A equal to singleton Y mean Y belongs to V, so that they are disjoint. So, hence every regular space is also a Hausdorff space. So, and similarly we define a point and a closed set can be separated. Now, still stronger is we have two closed sets. Here also we will assume that our topological space is a T1 space, then this T1 space is said to be a normal space or normal topological space if and only if whenever A and B are closed sets which are disjoint, then there exists open set U containing A and another open set V containing B such that they are disjoint. Then we say that such a topological space, we say that it is a normal space. So, what is called, these are the in fact important concept in topological space. So, a normal space, a T1 topological space is said to be a T1 topological space is said to be a normal topological space or normal space if and only if it satisfies the following condition, namely whenever A comma B are disjoint closed subsets of X, then there disjoint means A intersection B is empty. Whenever A and B are disjoint closed subsets of X, then there exists, whenever A and B are closed subsets of X implies, okay, just we will write implies there exist open sets, here just we say that A, B are disjoint closed subsets of X imply there exists open set U comma V in X. So, we have A comma B are disjoint or disjoint closed subsets of X imply there exist open sets u comma v in X such that U is a open set containing A. So, here this open set U should contain the set A. A is subset of U, B subset of V, that is first condition, and they are disjoint. U intersection V is empty. So, then we say that this such a topological space is a normal space. In fact, it is interesting to note that even a metric space has this strong property. So, in fact, we have a nice result, namely under what condition a given topological space is metrizable. So, metrizable, there we will see that if a space is essentially the minimum, if it is a metric space, mean it is a normal space. So, if it is so, a topological space is metrizable, mean it is essential that it should be a normal space. So, in addition to that it is a normal space, if we assume another much stronger condition, namely it is second countable. So, that is normal plus normal plus second countable implies it is metrizable. That is X tau is normal, I mean a topological space has this property. So, implied is metrizable, that is there exists a metric D on X such that the topology induced by that metric will coincide with the given topology. In such a case, we say that the topological space is metrizable. So, here what is easy to give is examples of a topological space which is not metrizable is easier. So, just to give a example of a topological space which does not have this property. So, even if it is not Hausdorff, here what is interesting to see here is we have seen that normal T4 that imply regular T3 that imply Hausdorff that imply every singleton set is closed. So, even trivial example, a space is not even T1. So, then actually it is not like T1, but not T2, like we have seen that even X is an infinite set, the cofinite topology is T1, every singleton set is closed, but it is not Hausdorff. But little other non trivial examples are the other, even if it is we want to give an example of a regular that is Hausdorff, but not regular. So, that is relatively not that easier. Similarly, a regular space, but not a normal space. For example, just again we will leave that, at least we will give an example of a topological space which is Hausdorff but not regular, and these things, all these examples we have discussed in our notes. So, we will have that is Hausdorff but not regular, half-stop but not regular. So, we consider our X is R, on R itself. Now, we will introduce another topology X equal to R. Consider the two type of open set. One is our usual open A comma B. This is a type, let us say a type 1 basic open sets, basic open set. A type 1 basic open set is of this type, type 1 basic open set. So, the type 2 is A comma B belongs to R, A less than B usual, and we consider this set all, we call it K, 1, 1 by 2, 1 by 3, 1 by 4 dot dot means 1 by n etc. This is a countable set. Now, type 2 open sets are basic open sets are from an open interval essentially towards open set containing, see if it is a neighborhood of 0, if in the neighborhood of 0 for large n 1 by n, 1 by n plus 1, 1 by n will belongs to a neighborhood of a normal usual neighbor. If it is a neighborhood of 0 means we know some minus r2 plus r the right side, 1 by n, n is such that 1 by n less than r, then 1 by n 1 by n plus 1 n plus 2 all are in this neighborhood. So, in such case we remove all those 1 by n's, then they are also basic open sets. So, the second type of basic open set is open AB difference K, correct. So, these are all, then this collection together, that is our script beta is say that script beta equal to set of all open sets of the type open AB, then open AB minus K, say that A comma B, see this A and B belongs to arbitrary A less than B, the set K is fixed. This such a collection will form a base for a topology on R. That topology we call it tau beta or K topology, normally it is known as K topology. So, this is okay known as K topology. So, here, so it is easy to see that this set A equal to 1, 1 by 2, 1 by 3 etc. is a closed subset of this K topology, is a closed subset of R with tau K. Let us call this as tau K. So, closed subset of this topological space, and 0 is not in A. See, note that this is A is not a closed if it is a subset of R with usual topology, but here we have in fact number of open sets are larger, I mean more than, see this is weaker than, which is our usual topology is weaker than this, because all the basic open sets are also here open sets. So, this in fact what is, if tau is the usual topology on R, then tau will be a subcollection of tau K. So, A is closed here, 0 is not in A, but now this then we cannot find a open set U containing 0 and a open set containing A such that they are disjoint. So, this is an example of a topological space. This R tau k is Hausdorff but not regular. In fact, another still non-trivial example is we can see that RL R suffix L. In fact, what is interesting here is if a regular space, the product of regular space is R suffix L is regular, hence the product space RL cross RL is also regular, but it will not be normal. This is regular. Again, this is a non-trivial example. It is a regular but not normal. See, that is, yeah. So, yeah. So, we will have in fact again, so that is easy to see that x tau regular if and only if for x in x and U open set containing x, for x in x U open set containing x, there x is on open set V containing x such that the closure is subset of U. See, this we can, so you are given a x in x U open set containing, for x in x U open set containing x. So, the complement A equal to U complement is a closed set and that x is not in A. Now, use the definition. So, then we will get a open sets separating the point x and the set A which is U complement. So, using that we will get a V having this property. Now, let us again quickly see that again a non-trivial example of a topological space which is not metrizable. So, I mean quickly we will see that a topology, consider this topological space R power omega which we have seen earlier, that is each element is a sequence x1 set of all x1 x2 x3 such that each xn is a real numbers. I mean this we call it essentially that is R cross R cross R, each the Cartesian product. Now, we consider here in fact R power omega with the usual, that means product topology. If you give the product topology, you can prove that it is metrizable. It is like countable number of times. Here also if the J is uncountable set, then even the product topology is not metrizable. Here we will prove that with box topology this is not metrizable. Tau suffix B box topology on R power omega. So, now we have seen that suppose if it is metrizable, in particular it is first countable. So, hence we have seen that an element x is in A closure if and only if there is a sequence in A which converges to x. So, we will construct a set A in such a way that and a point will give and no elements, and no sequence, I mean we will not get a sequence in A which converges to that point x, where x is in A closure. So, this proof is we construct all those A1, A2, A3 which are all strictly positive, all the AK is strictly positive for all k belongs to N. This is our set A. So, A1 positive, A2 positive, etc. this. Now, we will prove that which is our point. So, you take any here, because what is our basic open set can be, what is our basic open set in the box topology is, it is of the type pi u n n1 to infinity. So, each u n is open in R. So, with respect to this box topology, we will prove that say an element this, let us see whether 0 0 belongs to r power omega, but is in the closure. So, claim this 0 0 0 belongs to A closure. So, that means how to prove, take a basic open set containing 0 0. So, let capital B a basic open set containing 0, that means it is of the type A1 comma B1 cross A2 comma B2 cross A3 comma B3 cross, etc. A basic open set, a basic open set containing 0. Then what we have to prove is this set intersection with A is non-empty. So, here see that, so we have A1 more generally, it is a open set containing 0 0 here means containing 0 0 0. So, on each AK BK open set containing 0. So, that means 0 is an interior point. So, 0 is this open AK, BK is an open set in R with usual topology. So, 0 belongs to this interval mean there exists a an R greater than 0, so that minus R plus R will be completely inside A. So, now we can take an element say B1 between 0 and Bk or even Bk by 2. So, Bk should be positive. So, because 0 belongs to, we call it this open interval is inside Bk. So, we will get B1, B2, B3 which will belongs to B and all are positive. So, hence this B1 by 2 because of this open will take it still smaller. This is our, so we will write. So, that is we get, because we want that it should be in B1 by 2, B2 by 2, okay, dot dot, this belongs to all are positive, it is A, intersection we want it is here. So, that is why we have taken B1 by 2. So, it is intersection, okay, we will write pi AK BK, K varies from 1 to infinity. Here in each interval BK by 2 is there, correct. So, this set for each basic open set B intersection A is non-empty. So, hence for each basic open set B, intersection with A is non-empty, correct. So, this will imply this 0 0 0 belongs to closure. So, now you give, let us prove that you give any sequence in A, it cannot, it will not converges to 0 0. If it were, even if it is first countable, then there should exist a sequence in A which converges to this element 0. So, let us take take any sequence, let us call A suffix n. So, notation we should be careful, let us say A superscript n, n1 to infinity be a sequence in our set A, correct, be a sequence in A. So, it is each an is an element in A, hence that is A1 means, so now A superscript n belongs to capital A implies an is an element in r power omega. In particular here will, okay, let us say A1n, A2n and so on, because it is a, this belongs to A, I mean in particular it belongs to r power omega, because it belongs to A mean each is positive. Now, what is our aim is, you give, suppose this construct here the when A1, so we will have A11, forget about other thing. So, now we will construct this A11, so construct this, if necessary we can make it still smaller, A11 from the first A1. For the second we will have A2 mean A1 2 comma A22 and so on, this element A22, correct, comma A33 etc. So, now this will be an element in, now what we want to give is, give a basic open set, see we want to claim is what, an does not converges to, our claim is the sequence an does not converges to 0 0 etc. So, give a basic open set containing 0 0 such that no element of no an is in that open set. So, that means A1 is not in that set, So, what will be the, so let the basic open set, let us use this, let capital U, we will take care that it is a open set containing 0. So, we want that A11 is positive. So, we will take from minus to plus, see we have avoided, now A11 is not here. So, because it is open, even if you want even divide by 2. So, but this is sufficient because A11 is will not be in this set cross minus A22 comma A22 cross etc. minus ANN comma ANN cross etc. This is a, let U, then U is a basic open set containing 0, hence if the sequence AN converges to 0 will imply after some stage all the members, that means we should able to get that A superscript n, correct, that is what we have used that, okay, without bracket. So, A n should belongs to U after some stage. See, but here no element will be here because A1 will not be here because the first A11, so that should be, it is not here. Similarly, A22 is not here and so on. So, this sequence will not converge to 0, I mean this is an arbitrary sequence. So, that is there cannot exist, this sequence is such that AN is such that the sequence AN does not converges to 0 0, imply it is not even first countable. This will imply or omega with box topology is not first countable, is not even, is not first countable and hence it is not metrizable. In every metric space is first countable. Also it is easy to see that every metric space is normal, which is easy to prove that every metric space is normal, and there are, that is what this type of things are, if r power omega with box topology it is not metrizable, whereas with product topology it will be metrizable. Now, what is our main aim here is, see, we started with an abstract concept called a collection of sets, that collection is closed under arbitrary union and finite intersection. Such a collection we call it a topology on the given set X. Then we have seen properties which are related to open sets. See, like what are the properties related to open sets. So, we have X tau topological space, each member of tau is called an open set. Then we have seen that a concept, okay, even again we see only important, like when you say a topological space, for example compact, it depends only a open cover, a collection of open sets which covers capital X, then finitely many members of that script A will do, that will cover X. So, it depends only on open set. Then we define what is called connected. So, connected again not connected in a way, or if, or we can, if a space is connected mean we should be able to prove that the empty set and the whole space, these are the only sets which are both open and closed. Even closed mean again the complement is open. So, any related it involves only the open sets. So, connected using only again open set. Just now we have seen the other properties, second countable or first countable, all these things. What do you mean? Second countable. So, here again we have a base, I mean a subcollection of tau which is countable, then we say it is second countable. Then separable mean a countable set, countable subset of X such that the closure, again the closure of A, I mean closure again depends upon only open set. If X is in A closure mean you give any basic open set containing X, then U intersection A is non-empty. So, then separable mean you should get a countable subset A such that this set is countable. So, like this all these properties are related to open sets. There are still other properties, and like in any concept, when we say that two topological spaces are for all practical purposes they are same, that means that we call it a homeomorphism. If there is a homeomorphism between a topological space x tau and y tau prime, this is a homeomorphism. That means the map there exists a map from x to y such that f is continuous, f is a bijective map and inverse also continuous. That means a set A is open in x mean f of A is open in y, and if a set is here the other way, A is open if and only if f of A is open. So, this is a homeomorphism. In fact, a property is called a topological property, mean it is preserved under homeomorphism. Like we have seen that continuous image itself in a of a compact set is compact. So, it is a topological property. Connected, continuous image of a connected set is connected. So, it is a topological property. So, what about separable? Separable we have f from x to y, A separable, A mean A closer equal to the whole space. Then because it is a bijective function, f of A is A countable mean f of A is countable, because there is a bijection between these two sets. I mean you see and then it is a homeomorphism, that will imply f of A closer equal to f of A closer equal to f of A whole closer, but A closer equal to x mean this is capital F x. So, that is y. So, again f of A is a countable subset which is that will imply y is separable. So, like that we will have all these properties which are preserved under homeomorphisms. So, as a even for topologically we have seen that there is a homeomorphism between open 0 1 and any large interval. So, that means there is no difference between open 0 1 and any open interval. In fact, also there is a homeomorphism between R and open 0 1. So, if you have a curve like this, the endpoints are not included, then take even a line. So, we can have a bijection between this curve and this line open. So, there is topologically there is no difference between a curve and a line. So, like they are all topologically same, we can define a homeomorphism between these two spaces, and if you have a topological space x tau and y any set and here f is surjective map onto, then we can define a topology on y here such that yes u subset of y if and only if the inverse image is open in x, that means this belongs to tau. So, this will induce a topology on y, that is called Coulson topology. The idea is, so you can x is a set, we can identify and say that x for x y in x, x is related to y. So, then that relation is an equivalent, I mean you identify, see for example, if we have the open, consider the disk x in R2 such that we have seen that length norm x mean norm of order pair x1 x2 square, this is under root of x1 squared plus x2 squared equal to 1. If we consider this, then take all this element inside open interval x comma y, identify with singleton, they are related to only itself, but all the element if you say x squared plus y squared equal to 1, then all this element on the boundary you identify as a single element. So, then what we will get is, we will get a the sphere. So, that means if you identify all the elements in the boundary as a single element, and here each in the interior as they are all separate element, then so we have a bijection, I mean from that space. So, if we call the new space as y, then we will have a natural way, I mean all the elements in the boundary will go to one single element. If an element inside the image is itself, then there is a bijection, I mean sorry onto map, then here we have a topology, then we can define a topology on y. With that it is called a Coulson space, or we identify, that is what if you have a paper square, all the elements in the interior if I make it same, if you identify this point is x comma 0 and x comma 1, if you identify this paper you fold it, you will get a cylinder. So, like these are all called Coulson spaces, and so because of time we will stop at this stage. So, the rest of the things we have included in the notes. Here our main aim is to make a beginner who is not an expert in topology to understand the basic concept and then read the notes. Okay. Thank you very much.